Hi everyone, and thanks for joining me today, and thank you to Texas Cyber Summit for inviting me to speak today. My name is Connor McGarr, and today I wanted to take a closer look at automation from a red team perspective by really taking a deep look at rolling your own framework for initial access dropper generation leveraging C#, while maintaining the ability to leverage more custom shellcode loaders. Additionally, we'll take a look at the benefit of creating more custom loaders in order to evade kernel mode detection logic and achieve remote process injection without actually spawning any new remote threads. And with that, let's go ahead and get into the agenda for today's talk. So we'll begin this talk by going over why we would want to create an entirely new framework. We'll go over the architecture of our maldoc. We'll talk about how to perform remote injection without spawning remote threads. We'll talk about automating this with C#. We'll talk about a tool I created that incorporates everything we'll talk about today into a tool called Little Corporal. We'll give a quick demo, and then before we end, we'll allocate some time for some questions. Before we get into today's talk, let's begin with the obligatory Who Am I? So, my name is Connor McGarr, and I'm a red teamer here at CrowdStrike. I'm pretty much passionate about anything offensive Tradecraft, but more specifically, I really like binary exploitation and vulnerability research, specifically on Windows systems. I maintain a blog where I talk about many of these topics. So let's begin today's talk by going over why we would want to create an entire new framework. So, if you're in the red team consultancy space, red teaming, or any consultancy space for that matter, you know that it's high octane. So we're constantly keeping up to date with adversary TTPs, we're mimicking those TTPs, constantly doing research and evolving as red team operators. We also are constantly rolling on to new engagements and rolling off of old ones. So we're in a ton of environments that are quite diverse, and we're in those environments every few weeks. So, with the fact that we're managing so many different operations, it's a no-brainer that we need to automate some of the infrastructure of a red team engagement. So today we'll talk about automating the initial access dropper piece. But the main focus here today is, if you talk about integrating a custom capability, that infers that automation may not be possible if the capability requires some kind of custom or low-level understanding. So with that, if we would like to automate, there are pretty much two options here. We can either leverage an existing open source framework and integrate a capability, but with that, we're relying on the support of the creator of that project, and if not, you may need to become the supporter of that project, and there may be a lack of support for some features you may need, or we can just roll our own, which we'll talk about here today. So, creation of this automation framework, this is not a comprehensive list, and this is just a list that I arbitrarily put together. Everyone is going to have different experiences. This, from my experience, is what I look for in an automation framework. I look for the ability to write it in a high-level language that's easily understandable and is common. I look for the fact that this language we're writing in has integration with whatever dropper mechanism we want to use. So in our case, we want to generate some Microsoft Word documents. So C# has the ability to integrate with the Office API to programmatically do this. We want to be able to support any C2 framework. So essentially, we don't want it to be specific to one C2 framework. If a C2 framework can create shellcode in order to generate the artifact used for the engagement, that is what we need, and that's what we should be able to support and keep it C2 agnostic. And then we want the potential to always be improving through modularity. So now let's get into the architecture of this maldoc by outlining the objectives and what we're looking for here. Again, to reiterate, this varies across operators and what various operators, adversaries, or whoever deems as what's needed for a given engagement. For me, this talk, these are the things that I look for in the architecture of a maldoc, and so let's go ahead and get into that here. So the maldoc obviously needs the ability to persistently store the payload we would like to execute. And this normally comes in the form of a reflective DLL that's ported to shellcode. We want the ability to decouple execution of the payload, so we do not want the payload to be running directly within the word.exe process, as this is an IOC for blue teams. Additionally, we want the ability to integrate a custom loader and avoid these common Windows API calls, the chain of calls, I should say, of allocating memory with virtualx, write process memory, and then creating a remote thread. We want to try to avoid these more popular injection techniques. So kind of answering these questions, for our purposes, the way that we will actually persistently store the payload artifact is through the inline shape.alternative text word property, which we'll talk about shortly. The way we decouple execution of the payload is we will use local injection to actually execute the remote injection capability, which will remotely inject our C2 payload into another process. This may sound kind of confusing, but we'll get into the lower level details here shortly. And then integrating the custom loader, we want to use a technique known as thread hijacking, which essentially will locate a remote thread within a remote process, hijack that thread in order to execute our shellcode, and then restore execution of the thread. This avoids new remote thread creation. So beginning with how we're going to store our payload, let's talk about inline shape.alternative text word property. So this is a property in Word, as we can see from the screenshot on the right hand side, which sets a string that represents the alternative text associated with a shape in a web page. For our purposes, this will be an image that's pulled down remotely from the internet into our document, and then we can use this property in order to actually store our full payload there. So basically, if you have the ability to embed an image into the document, you have a way to store the payload with the architecture of how our maldoc is going to look. So with the ability to store the payload persistently, the goal now is to perform the loading of the payload that we've stored in memory. And for our purposes, we're going to use process injection. So just a quick brief word on process injection. If you're a red teamer or a blue teamer, you know that this is highly scrutinized. So I just want to put that out there. Having said that, there still is a time and a place for process injection. For example, if there's a brittle detection that relies on a known good, such as we can expect only a given process of XYZ name to perform a given action, that can be circumvented by getting in context of these known good processes through process injection. So for instance, if we deem a certain process as always doing something that's benign, which again is not a very good detection, but this is something you do see, if you're able to get in context of this process by performing injection, you then may be able to blend into the environment more readily. And again, process injection is not always nefarious, so there are legitimate reasons why process injection takes place. One of the reasons, as we'll see shortly, are browsers that map dynamically generated machine code through a process called just-in-time compilation into a renderer process which a user interfaces with. This is done through what's known as out-of-process JIT engines. And again, as underlined, there is always room for improvement. So this talk outlines the beginning of leveraging more custom loaders. I'm not going to say that the loaders we will show have never been seen before. There are plenty of cases that are public with these loaders available, but they're less well known. And because of this, each technique needs to be vetted and studied for the indicators of compromise that are left behind and adjusted accordingly for better OPSEC. So with that said, let's talk about how our process injection will look. Our process injection will be twofold. So we'll begin with an initial local injection into the word process. So this injection will actually load a second stage, which is actually going to be a full C#.NET assembly, which has the capability to perform remote injection into the target process. And again, our payload here does not necessarily have to be C#. That's just what we're using for the purposes of this talk today. The reason why we want to perform local injection is twofold. One, we can decouple execution. So the final payload will not actually run within the word process. Injecting to the word process is just simply a means to an end to perform remote injection. Also, local injection is less scrutinized than remote injection. It's a lot harder to detect. So everything that's loaded into memory will be loaded into memory through the local injection before any remote injection is performed. And so now that we have some primitive to actually perform remote injection, a la our local injection into the word.exe process, this gives an operator extensibility into the ability to choose a process which perhaps may blend in better within the environment. So think about earlier what I spoke of with brittle detections that just purely rely on a given process name. But again, this is highly dependent on the target environment, and this actually falls more under conjecture versus data that can back this up. So starting with the local injection into the word process, we know that we're going to have a .NET assembly which we need to inject locally. So in order to do that, we need to first convert this .NET assembly into position-independent shellcode. And the way we do this is with an open source tool called Donut. So I'm not going to get into the technical details of Donut. If you would like to do that, the Wover has a beautiful blog post bringing Donut to light and explaining how it actually works. But for our purposes, just know that Donut converts a .NET assembly and more technically into position-independent code, which then can be used for injection purposes. So, after we use Donut to convert the .NET assembly which performs the remote injection, we can actually load that into memory using a simple VBA macro which calls a few Windows APIs. So first of all, the payload is first base64 decoded, because in the future we will be encoding this in base64, and it's stored in the inline shapes.alternative text word property. And so what we do is, using the VBA macro, we index the inline shapes.alternative text property from the image that we've stored. We base64 decode it, then we perform local injection using virtual alloc and create thread. Again, as I've mentioned, with remote injection with injection, there's always room for improvement. This is just for the purposes of the talk today and to outline a proof of concept. So this all may seem very confusing thus far, but let's talk about the actual execution flow. So as we mentioned, local injection first happens into the word process. So as we can see in the screenshot, the .NET assembly is actually loaded into word.exe. And once this .NET assembly is loaded into Word and it's executed, the .NET assembly actually performs remote injection into a specified process by the operator. In this case, it would be msedge.exe, which is Microsoft Edge that runs on the Chromium engine. So now that we kind of have a clear picture of what our goals are, and knowing remote process injection is not only the end goal but is highly scrutinized, let's formulate a remote process injection technique. So our base condition for the purposes of this talk is that remote thread creation is a great indicator of compromise that can be used to detect remote process injection. So knowing this, let's talk about remote injection without the need to create new remote threads. So as a quote-unquote mock sensor, we will use kernel mode telemetry as a target to bypass some detection logic. So I won't get into the full details here, but within kernel mode, you have something on the Windows operating system called the kernel mode callback table. And these are basically arrays of functions that are called when a certain action happens. So in the screenshot below, we see that the kernel callback table here is called PSP, create process notify routine. As the name suggests, anytime a new process is created, all of these functions here would be called. So indexing this array and performing a few bitwise operations to actually extract the memory address of a registered function here, we can see the TCP IP driver actually registers a function called create process notify routine X, which again is one of those functions that is called every time a process is created. So building off of that, we have another one of these function callbacks called ps set create thread notify routine. And this is kernel mode telemetry that detects any time a new thread is created. And so what our mock sensor will do is compare the injector and the injectee process to determine if they are different. If they are, we can infer that remote injection has occurred. So if we take a look at the screenshot here on the right hand side, this is a test quote-unquote mock sensor I wrote for the purposes of this talk. And all it does is register a user-defined function into that kernel callback table to detect every time a new thread is created. And then what it will do is it will say, hey, is the current process different from the process that created the thread? If it is, we assume that this thread was injected by a remote process, thus indicative of remote process injection. So as we run the mock sensor, as we can see below, we can see that there are many false positives. The example below, as we mentioned earlier, an out-of-process JIT server is mapping compiled code into a browser renderer process. So JavaScript is an interpreted language. But there's something known as just-in-time compilation, which is used for performance benefits. Interpreted languages are much slower. So what happens is if a certain JavaScript function is constantly called and called and called, it becomes what's known as hot. And when that happens, there are varying degrees of optimization that a just-in-time engine will take in order to actually compile that code into machine code for performance benefits. And so because you have an out-of-process just-in-time server, it actually needs to perform process injection to map that optimized code into a renderer process. So we know that there will be many false positives, but this is what we call our baseline condition. So this baseline condition makes an inference about remote injection, which we spoke of earlier. That remote injection always results in a thread that's created by a process that is different from the process the thread was housed in or created. So if we think of our standard remote injections, such as create remote thread, APCs, or similar APIs, these all rely on creating a new thread within a remote process. And this condition would be true at the kernel level, as we've seen. So there could be many more detections that are built off of this baseline condition in order to minimize the false positives that we see here. However, as a quote-unquote last line of defense, this baseline condition should always be true, therefore detecting remote injection if all of the more fine-grained detections are circumvented. Knowing this, as an adversary, we want to target either the baseline condition or the telemetry source itself. If we conveyed this baseline condition, the sensor will then just simply gather the telemetry of the thread creation and be done with it, and it won't actually alert. But please note that a sensor sees everything, and this telemetry could be used as the basis for future detections. The point here is to outline what I myself consider an evasion opportunity. This depends and varies on who you ask what their definition of evasion or bypassing is. But for me, what I view as an evasion opportunity is not tampering with the sensor in order to neuter it so it cannot see telemetry, but find weaknesses, not based on conjecture, but actual data, and take advantage of it. So in this case, how the sensor is actually detecting remote injection, that is what we would like to directly attack. So that just is my little spiel on detection and evasion. So, excuse me. How do we avoid this detection and attack that baseline logic for evasion? We can actually do this through thread hijacking. So instead of creating a new remote thread, let's see if there's not a way to use an existing remote thread. So, as I mentioned, instead of creating a new remote thread within a remote process, we can simply identify an existing remote thread, suspend it, update that thread somehow to force it to execute our shellcode, and then resume the thread. I released a blog that has more comprehensive technical details on this TTP that can be found here. We'll go over at a technical level everything, but not as in-depth as this blog due to time, for time's sake. So the first thing we need to do is target a remote process. So what process would we like to inject into? For our purposes, this can be anything, but what you need to do once you've targeted this process is open what's known as a handle to it. So a handle basically is a kernel mode object that allows one process to intermediately interact with another process. That's very simplified, but for our purposes, since a handle is an object in kernel mode, we can't directly, since, excuse me, let me rephrase. Since processes are kernel mode objects, we cannot just directly access them. So what we do is we need some kind of intermediary way to interact with that process, and we do this through a handle. Since it's a kernel mode object, we can't directly just start interacting with other processes. This is the way that we need to do it on Windows. So once we have the ability to interact with that process through a handle, what we like to do is call a few Windows APIs in the screenshots here that basically will loop through the threads on the system and break upon encountering a thread, the first thread determined within the remote process we're targeting. And then once we've identified the thread that exists within the remote process that we want to hijack, what we need to do is put the thread in a suspended state. This is required for modifying threads. They need to be suspended, generally speaking, first. And these are the Windows APIs that we do it. We first actually need to open a handle to this thread, and then once we do, we can suspend it. So at the current point, we have a remote process that we've targeted, and we have a thread within that process that we've suspended, and we have a way to interact with that process and interact with this thread. So a thread is also an object that's managed by the kernel, and it has an associated context. And basically a thread's context is a representation of execution at the time the thread was executing. This is represented through CPU registers that the thread uses for execution. Recall, each thread gets its own stack. And this context is represented by a context structure on Windows. So as we can see from the screenshot here, this is a context structure on Windows. It's a bit truncated. But as we can see, these are the various CPU registers that we are probably all familiar with. We can see the stack pointer, the instruction pointer, and the various other things like the accumulator, etc. So we know that a thread has an associated context that represents all of its CPU registers. We have a way to interact with the desired thread. So what we can actually do is call another Windows API called getThreadContext, which will actually retrieve an associated context structure for a given thread. And so what we can do here is actually get the context of the thread we would like to later hijack. And just a little spiel on Windows memory. So the address space on Windows systems is private on a per process basis. So each process essentially has its own private mapped view of memory. And if you want to take this further, you can open up a kernel mode debugging session and change the value of the CR3 register, which contains basically the base memory paging structure, in order to investigate this more. But with this in mind, we know that each process has its own privately mapped view of memory. So if we have a given payload, if it's stored within the local process, the remote process is not going to be able to see that, which is our target process we want to execute in. So the first step is, once we've actually captured the context of our thread, is actually to inject the remote blob, which in our case is a Cobalt Strike stageless shellcode blob. We want to place that in the remote process. We're not executing it, we're just placing it in the remote process for future use. And the way we do this, again, everyone has seen these function calls before. You have virtual alloc x and write process memory. And again, as I've been reiterating, this can be changed, these can be updated, these can be improved, how we actually call these functions. So once the payload is actually stored in the remote process, the goal is to eventually execute this payload. So what we want to do is we want to inject a huge, not necessarily huge, it will be big, but the goal is not for it to be big. What we want to do is inject a first staged shellcode, essentially, that we'll call create thread in context of the remote process. This is because the Cobalt Strike beacon payload, for our purposes, this could be any payload, we want it to live within its own thread. And the way we do that is by using a call to create thread. Like I mentioned earlier, local injection is much less scrutinized than remote injection, and it's a bit harder to detect. Excuse me. And because of that, we want the API call to happen in the remote process to create a local thread in context of the remote process. So the way we do this is actually at the assembly level, we'll write some custom opcodes, basically custom shellcode, that will dynamically call create thread while supplying the beacon payload as the routine we would like to execute. So the way we do this first is we need to see how create thread is actually prototyped. And this can be viewed on the through Microsoft Docs, formerly known as MSDN. And we see a bunch of parameters that this function expects. The main one we want to focus on is this LP thread start routine, which is a pointer to a function that's to be queued for execution when the thread is created. And again, for our purposes, we are assuming a 64-bit system. And with a 64-bit system, we then assume what's known as the fast call calling convention on Windows. So the first 4 arguments for a given function that's called through this calling convention, for our purposes, are passed through these registers: RCX, RDX, R8, and R9. Every argument after that is passed through the stack, similarly to standard call, which uses a stack for passing arguments. But we start at an offset of 20 on the stack, and then every 8 bytes afterwards. So, knowing the calling convention, here is how we would need to set up our call to create thread. These are the various parameters that it expects, and these are the registers we use to pass the arguments. So what we do is we create a shellcode routine. In this case, it's called create thread. And what we also do is we perform a typecast on the previously allocated region of memory we use with virtual alloc x in order to cast it to an LP thread start routine. And so that begins the process. I included this slide for the purposes of the engaged viewer or reader. I'm not going to go through this verbatim. It's here and it's heavily commented, and it's also available on my GitHub if you would like to look at it. But just at a high level, as we can see through the comments, we start with the RCX register and we work our way down in order to satisfy all of the function calls through custom opcodes. So when this would be executed, it would call create thread at the assembly level within the remote process. So now we have a piece of shellcode that, when executed in context of the remote process, will spawn a local thread that houses the beacon implant. Knowing this, though, in order to execute the code, what we actually need to do is perform the thread hijacking to kick off this execution, right? And the thread hijacking is going to rely on corrupting that previously captured context structure. Because we will be manipulating it, and when the shellcode is actually executed, the state of the CPU registers will be basically foreign at that point, and it will cause a crash of our thread because we're invalidating the integrity of that context structure, and the CPU registers will be haywired essentially. And when that thread crashes, in all likelihood, it's going to cause the process housing that thread to also crash. So what we need to do is we need to bake in a routine that's appended to the shellcode that calls create thread that will handle this and will resume execution. So there is a beautiful function on Windows known as ntcontinue, and it's used to resume execution after an exception. And knowing this, we can actually use this functionality to resume execution automatically. So with ntcontinue, we need to pass it a context structure of essentially the context we would like a given thread to resume, right? So this ntcontinue call will happen in context of being executed by this remote thread. So this is all very confusing, and it will make more sense in the future. But essentially, if we think about it hard enough, we're taking a remote thread that we've enumerated within the remote process. We're corrupting that context structure in order to point it to our custom shellcode. So this shellcode is actually being executed from the remote thread. It just was not remotely spawned but artificially by us. So knowing this, if we can make a call to ntcontinue, which will resume the calling thread essentially, this is actually the remote process, the remote thread that we hijacked earlier, right? So knowing this, ntcontinue accepts a pointer to a context structure that is to be resumed by the calling thread. So basically, ntcontinue is going to say, hey, thread, I see that you're passing in this context structure. I know that's how you would like to be resumed. Let's go ahead and update that for you. And this is going to happen after the call to create thread. So remember, again, the address space on Windows is private. So from our quote-unquote exploiting process that we're performing this capability through, that address space is it's the same essentially in terms of what's mapped, so ntdll, kernel 32, etc., but it has its own privately mapped view of that memory. So the context structure right now is within our current process, the quote-unquote exploiting process. That's where that context structure lives. So since the address space is private, we need to first inject it into that remote process. So the remote process has a way to pass the pointer to that structure to resume execution. So after that long-winded explanation, the call to ntcontinue would look like this at the assembly level in the fast call calling convention. We pass the context that we would like to resume, and then there's a bool that can also be passed here, which we don't necessarily care about for our purposes at the current moment. So after we've injected that context structure into the remote process, we know that this remote process will then be executing the opcodes we see on the screen. So in the RCX register, we locate where that context structure is. We pop it into the RCX register essentially, and then we set the RDX register to false by XOR operation. So now we have a way to spawn a local thread to house the beacon implant, and then we have a cleanup routine after that. But we also want to make sure that the stack is first 16-byte aligned before we make any API calls. The reason is this is the fast call calling convention requires the stack to be 16-byte aligned. And so all we do basically is we prepend everything with a bitwise AND operation that will basically make sure the stack is 16-byte aligned and that we're good to go. And so now that we have that long-winded explanation of the shellcode blob we want to execute within the remote process, the last step is actually to kick off execution of this. And so what we do is that previously captured context record, this is now where we corrupt it and we hijack it. So the instruction pointer on Windows, or any CPU for that matter, is responsible for the currently executing instruction. So whatever's loaded in the RIP register, that's what the program is going to be executing. And so what we do is we take that RIP member, the instruction pointer, and we actually corrupt it in order to force it to point to our previously allocated shellcode. So as I mentioned, we inject all of this capability into the remote process. There's a memory address which corresponds to this large blob. We update that RIP member in order to point it to our user-specified shellcode blob. So what happens is when this thread actually resumes, the RIP member will be pointing to our shellcode. And so execution will kick off to our shellcode. So after updating the hijack thread, we resume the thread as mentioned, and that will spawn our execution. And so this all sounds very confusing, and this next image may look very confusing, but I'll walk through it, what that looks like. So here is how this looks in the debugger. So we first have a stack alignment plus create thread routine. So as we can see in this first outline box, this first call instruction, it calls this memory address. And if we look at what this memory address shows, it has our bitwise AND operation. It has the move R8 instruction, which again is that LP start thread routine, which we want the create thread function to execute. This is the start of the beacon payload, as we can see in the last screenshot or in the last box below, which is prepended with no ops. Once this executes and the call occurs, the next thing that happens is the NT continue routine is called. So we can see in the move RAX offset in the instructions below the call that happens, we can see that NT continues being moved into the RAX register, and then we call the RAX register. And when this call happens, this should resume execution of the thread, and the process should be usable. So after the components of the thread hijacking are placed into the remote process, the hijacked thread is resumed, and execution kicks off. We'll take a look at this in the final demo at the end of the presentation. But that's kind of how our remote injection is performed without actually creating a new remote thread. So how do we automate this all in C#? How do we put all these pieces together automatically? So we have a loader, a shellcode loader that performs remote injection that we just showed in the previous slides. And this is done in C#. So for modularity purposes, we can actually basically templatize the .cs file to allow an operator to dynamically specify a given process and the shellcode they would like to execute. So basically in the automation executable, it would look for the string replace one and update it with a user specified process, and the same with replace two. That would be replaced with the shellcode you would like to execute, which in our case was a beacon payload. As I mentioned in the beginning of the talk, we want to choose a high-level language that has some kind of way to interact with the mechanism for the dropper. In this case, we're using a Microsoft Word document. So C# actually exposes a way to leverage Microsoft interrupt objects to interact with the Office API. And so we start all this off basically by creating a new instance of Word within C# that we can interact with. So as mentioned earlier, we have a Word macro that will perform the local injection of the donut-generated shellcode, which basically is just a shellcode representation of our remote process injection .NET assembly. But in order to programmatically insert a macro into a Word document, you have to update a registry key in order to bypass the protection. So obviously if you're running this on a development machine, this is definitely okay to do because we need some way to automate the process of injecting that macro into the document. So we need to basically programmatically edit the registry in order to allow programmatic access to Visual Basic. Once that's done, we can actually create the Word document and obviously this is needed for us to write the macro to in a future step. So here we can call some interrupt objects in order to actually create the document itself. So after we've created the document, as mentioned, we first need to convert our C# loader into shellcode through Donut. So we actually automate this through sub-processes on C#, and the code can be shown below. So with this .NET loader that performs the thread hijacking capability now in shellcode, we then want to store this blob within the Word document. And as talked about throughout this talk, we do this through the inline shape.alternative text word property. So basically for a proof of concept, here we're just choosing a random blank image from the web, and then we're updating the alternative text to basically store our base64 encoded donut blob that we previously created. So the next step then is to templatize our VBA macro for local injection. So this is basically a template that won't change. It does the same thing. Base64 decodes the shellcode blob, which is retrieved from the inline shapes.alternative text property. And then it performs a local injection. So basically you take this VBA macro, you would then store it in a text file, and then in your automation, you would basically read in this text file and store this as a macro within the document. And that's exactly what we do here. So we look at this VBA underscore template.txt, we basically read in the template, and we inject this into the document. So this creates a weaponized Word document. So now that we've gone through all the steps, if only this was available for use already. Little cheeky here, but this is available for use through a tool that I created called Little Corporal, which is a C# automated maldoc generator. So as mentioned, this is a project that I wrote that automates everything shown. It performs thread hijacking via local injection of the .NET assembly through Donut, and it automates the document creation and VBA macro insertion. And it can be found on my GitHub as previously shown. So here's the help menu. Basically all you need is the shellcode you want to inject into a remote process and the name of a target process. And here's a quick demo on that. So here is how document generation looks. You specify the shellcode and the name of the process you'd like to inject into, and it's as simple as running it, and a Word document then is spit out for you. And then looking at the actual execution of this Word document, we have another demo here. So once the document is created, we then open the Word doc, and we can see that our Cobalt Strike beacon is phoning home under the process of Explorer, which we specified. Now, rerunning this POC to inject into notepad.exe to make things very clear, we can see that we've bypassed the detection logic of our sensor. So in this case, Notepad is running under the PID 5392, and in this case, our driver prints out every time remote injection occurs, and as we can see, there are no instances of this process ID. Notepad is still running, and if we look in the next slide, just for proof of access as good measure, we can see that we have a beacon phoning home with this process ID. So, to summarize everything we've talked about today, you do not have to sacrifice custom capabilities in the name of automation. Although it's not the path of least resistance in some cases, it is possible to create your own automation frameworks and then to keep those modular with those custom capabilities built in. With a modular approach, you can support other techniques for shellcode loading. So kind of building off of this, we have a Word document that pulls in a remote image and stores shellcode blob within that image through a property within Word. So if you're sending out a phishing campaign and you want your Word document to look more believable, you could host a remote image that is well crafted and use that not only as the premise for your social engineering for the document, but it also works in a second manner, a double whammy, in order to store your payload. And then additionally, almost a triple whammy, you could even take that further and collect phishing statistics if the Word document itself, when it pulls down that image, because it's specified through a URL, if you are the one hosting that image, you could additionally collect phishing statistics here. And as my old manager, Mike Felch, once said, creds are king. I myself say data is also king. So if we can understand how telemetry is actually gathered by a sensor, this is more useful to a red team for evasion purposes in the long run versus your more quote-unquote conjecture bypasses. So these conjecture bypasses, they may be something like adding a null byte on the end of an exe to bypass some signature, or some other action where you don't necessarily have the data to prove what you're bypassing. You're just kind of shooting in the dark almost. These may evade some of the more fine-grained detection logic that's very specific, but don't expect this to evade your baseline conditions or telemetry source in general. And then with that, I would like to just say thank you, and I am very happy to answer any further questions. Thank you.